Alright, in this lesson we will derive the formulas for satellite motion to determine the speed of a satellite, its acceleration, and then Kepler's third law, the law of harmony, ratio t squared over r cubed. Basically, all of these are going to be developed using the fundamental concept that for satellite motion, the force that is providing the centripetal force to keep it in circular motion is centripetal force is equal to the gravitational force. And then simply substituting the formula for centripetal force, the mass of the satellite times the speed of the satellite squared, and that's the tangential velocity, divided by the orbital radius, r. This is the formula for centripetal force. The formula for gravitational force is, of course, the gravitational constant times the mass of the object multiplied by the mass of the second object, which in this case would be, say, the sun. If you're talking about planets orbiting the sun, it could be the mass of the earth if we're talking about satellites orbiting the earth or the moon orbiting the earth. So divided by the distance between them squared. So what we want to look at, and I probably should have made the capital M maybe a little bit bigger to make it obvious. So in these formulas, the lowercase m stands for the mass of the orbiting object. And that could be a satellite, it could be the moon going around the earth, it could be the earth going around the sun, but it is what is actually in orbit. The capital M is the mass of the central object, and by that we mean the mass of the object which the other one is going around, mass of the central object. So the r in each of these formulas is the orbital radius, and when we talk about the orbital radius, that's the distance from the center of the central object to the orbit. Now, if you recall the other day in class, we talked about the word altitude. Altitude is the distance from the surface of the central object to the orbit. So altitude is measured from the center of the central object. The altitude is the distance from the surface of the central object up to the orbit. So when you read problems and so forth, you want to make sure that you're visualizing it correctly. In other words, if this is my central object, and that's its radius, and then I have something in orbit around here, and this is the altitude, then this from here to here would be the orbital radius, whereas the other was the radius of the central object. I'll just say r of m. And of course, the radius of the central object plus the altitude is going to be equal to the orbital radius, which is what you want to use in all the formulas, is the orbital radius. So looking at this, we can isolate and solve for velocity or the acceleration. So that's the basic formula that we're going to work with. Also, another formula that we'll work with is centripetal acceleration is equal to the tangential velocity squared divided by the radius. So that's another basic formula that we can use. We can also find the speed of an object by the object that's in orbit by multiplying or dividing its circumference 2 pi r by its period t, and notice that's a capital T because it stands for the time for one complete revolution. Now those are the basic concepts. So let's begin with developing our formulas. First we had Fc is equal to F grav m v squared over r is equal to constant mass of the smaller satellite object times the mass of the central object divided by the orbital radius squared. Now if I take this equation and solve for v, I'd first multiply through by r and divide by the lowercase m, and that would give me g m big M r divided by r squared, and then I also wanted to bring the m over on the other side. So all I did here was divide both sides by m over r, and that gets rid of it on that side. Taking the square root of both sides, we have our first formula, but look what happens with this r cancels out the square, the little m's cancel out. So we have that the speed of any object in orbit about a central mass of mass m is going to be equal to the square root of the constant, which is 6.67 times 10 to the negative 11 Newton meter square per kilogram squared. And if you look at your units, inside the square root you would have Newton meter square over kilogram squared times kilograms, all of that divided by meters. And so when I simplify this kilogram is going to cancel out this meter is going to cancel out that, and I'm left with the square root of Newton meter over kilogram. And a Newton is a kilogram meter per second squared, and that's multiplied by meters and divided by kilograms. The kilograms cancel out, and I'm left with the square root of meter square per second squared, and that of course is meters per second, which is the proper units for speed. So this is the formula for speed. Remember, the capital M is the mass of the central object. The r here is the orbital radius, and so the speed of any satellite in orbit around a given mass is going to follow that same formula. All satellites at the same orbital radius around an object will have the same speed. Secondly, we can very easily extend that to the formula for centripetal acceleration by saying AC equals v squared over r. Replace v with what it's equal to, which we just found to be the square root of, whoops, here's where I want to write that. Centripetal acceleration is equal to v squared over r. And so that would be, take the square root of g big M over r, square that, and divide by r. So you get g M over r squared by the time you divide that one. And that is your formula for centripetal acceleration for any satellite in orbit around that mass. And that takes care of this formula and this formula. Now, in looking at the ratio of t squared to r cubed, that is Kepler's law of harmony, let's go down and see what we can do with it. If I look at the period, we can make use of the formula v equals 2 pi r over t. Solving for t, I get t is equal to 2 pi r divided by v. T is equal to 2 pi r divided by what v is equal to. And we just had that up here. Let me show you where it's coming from. V is equal to the square root of g m over r. So if I put the square root of g times the central mass divided by r. Now if I square both sides so that I don't have any more square roots, I get t squared, squaring the top, I have 4 pi squared r squared divided by g times m divided by r. So when I simplify the right hand side, I get 4 pi squared r cubed divided by g m, and that's just invert and multiply by the denominator. Divide through by r cubed, and I have t squared divided by r cubed. That ratio found by Kepler is equal to 4 pi squared divided by constant times the mass of the central object. And that is the last formula. So going all the way back to the top, that's where this formula here comes from. So now we've gone through the derivation of each one of those, and as you can see, it's really not very difficult to do that math. In working these problems, of course, you need to know what the value of g is. You would have to be given this mass of the central object, like the mass of the Earth if it's something in orbit around the Earth, or the mass of the Sun if it's something like the planets in orbit around the Sun. That information would be given to you. I certainly wouldn't expect you to memorize those. The one thing that I do want to caution you about, though, is that the formula has an r in it, and you must remember that that r in each of these formulas is the orbital radius, the distance from the center of the central mass all the way up to the orbit. So if they don't give it to you that way, if they give you the radius of the central object and the altitude of the satellite, you'll have to add those together to find the r that you're going to use in your formula. Now, the work that you need to turn in is this worksheet that says Mathematics of Satellite Motion, and I want to show you, obviously when I was fixing this up, I ended up with 2 copies of this part here where it says check your understanding. I'm on page 3. This part up here at the top with the smaller writing of check your understanding, you can just cross that out and go to this one. I double pasted it somehow, but I didn't catch the very end of it. So you want to be sure that you do this third part. So if you just, no point doing it twice, you can just cross out that one at the top of page 3 and just do the larger part down here at the bottom. And that's that. You can turn that into Moodle as soon as you finish with it. It's my understanding that you're not absolutely required to have everything done until the day we get back, but the prudent student would probably want to go ahead and get them posted so you don't have so much to do at one time.